we are going to now discuss about fugacity, okay, and its particular role in phase equilibrium. So, for the ideal gas, we have already considered earlier or discussed earlier that fugacity is nothing but pressure for an ideal gas, right. So, for the pure system, so for component I in a mixture of ideal gas, one Fi will be Pi, where Pi is a nothing but partial pressure. Okay. So, this is partial pressure, Pi is nothing but partial pressure. Okay. Now, as we know that for all the system, whether it is pure or mixed, the approach to ideal gas at low pressure. So, in other words, Fi by Yip tends towards 1 by looking at this expression as P goes to 0, because at P goes to 0 the fluid starts behaving like ideal gas, and thus this expression holds. Now, what we are interested is basically to make use of fugacity in our phase equilibrium. Okay. The question is, can we replace chemical potential by fugacity, okay, by using transformation or some other criteria. So, fugacity, it turns out, is basically a convenient variable for fundamental equations of phase equilibrium. So, we know the fundamental equations or the conditions for phase equilibrium are right, okay, for two phases alpha and beta. Okay. So, let us try to make use of this equality of the chemical potential of component I. Okay. So, for mu I is equal to mu I b, I can write it as by the definition of the fugacity, this would be mu I alpha minus mu I 0 alpha. This is RT ln Fi alpha Fi 0, right, for a specific I. Similarly, I can do the same exercise for mu I beta okay. So, knowing this, that this condition should hold. So, what we do is we write this expression. Okay. So, mu I put it here and mu I beta I put it there. I get the following expression, mu I 0 alpha plus RT ln Fi alpha Fi 0 alpha. This should be mu I 0 beta plus RT ln Fi beta Fi 0 beta. Okay. So, I have this relation which connects the chemical potential in the reference state of alpha to beta and the fugacity ratios. So, what we are going to consider is two cases. Consider two cases. Okay. Okay. So, let us assume that for both the phases the reference conditions are same. Okay. So, that means reference potentials are same. So, we are going to consider case 1, where we consider that reference chemical potential of component I, okay, is same. If you consider this, since chemical potentials are related to fugacity, which essentially means Fi 0 alpha should be same as Fi 0 beta, and in that case this implies that Fi alpha should be same as Fi beta. Okay. So, this is directly, it implies taking this as assumption that this must be considered, that you consider the reference chemical potential to be same. Okay. Now, what is the second condition? Case second. So, suppose that standard states of alpha and beta. So, I am going to write this now. So, what is the case 2? The case 2 is, suppose that standard state for alpha and beta are at the same temperature, but not at the same pressure and composition, which means basically you cannot just take it mu as 0, alpha is equal to mu I 0 beta. Why? Because it depends on T and pressure 0 is there, the reference pressure is also considered. So, we have to now relate the chemical potential of reference state of alpha and beta. Okay. So, in that case, there is a relation between the reference chemical potential of alpha and beta. Considering the difference, we can straight away make use of the definition of the chemical or the definition of the fugacity. Okay. Now, this is the relation. Now, you can plug this equation into the basic chemical potential equality, and so you can show that mu I 0 alpha which essentially means, so plugging in mu I alpha is equal to mu I beta. This clearly shows, because this is nothing but same, okay, which means basically Fi should be equal to Fi beta. Okay. So, what it tells you, that the equality of the chemical potential can be replaced by the equality of fugacity or for a given component in two-phase system, or in general you can now represent the convenient fundamental equation of phase equilibrium. Which is going to be T alpha is equal to T beta, P alpha is equal to P beta, and Fi alpha is equal to Fi beta, where I is equal to 1 till n. Okay. Now, I am going to make use of this expression, and for a simple application, which is nothing but Raw's law. So, what we are interested is that for a arbitrary system vapor liquid at equilibrium, we are seeking a simple relation describing the distribution of the component between these phases alpha and beta. Okay, that means we are interested in to connect mole fractions x in the liquid phase and y in the vapor phase. Okay, so we are going to consider a simple system whose behavior can be approximated closest to ideal gas or ideal solution or ideal behavior. Okay, so let me just take component, let us say 1 in this mixture. So, F1 let us say is in the vapor phase should be equal to F1 in the liquid phase. Okay. Now, this is what we know as far as equality for a given temperature and pressure. So, what we are interested is basically connecting this and relating to the mole fractions and the other variables pressures, for example. So, what is the assumption here? So, let me just take assumption number 1. Okay. The assumption 1 is F1V at TP, constant temperature pressure, is proportional to the mole fraction of 1. Okay. In other words, we are saying F1V is Y1 vapor of pure. Okay. So, this is what we are trying to say, that this is proportional to Y1. Okay. Now, this is assumption 1. Now, we are going to take another assumption. So, this is assumption 2, okay, that f of L is proportional to x1. So, this is basically saying that these are all ideal solutions, okay, where the fugacity is proportional to the mole fraction. Now, remember this F1 pure in the vapor, this is at the same temperature and pressure of the mixture. Okay, same Tp is same. So in this case, for the case of assumption 2, what we are saying is that F1L is X1 FL pure 1 pure. Okay. All right. So this is again the liquid fugacity of the pure component in the liquid phase as temperature Tp. Okay. So this assumption says that this is basically an ideal solution and is reasonable for conditions where the components are of similar type. Okay. So let us put it in there in the condition of the equality of the fugacity. When you do that, we get Y1 Fy pure, this is X1 Fl 1 pure. Okay. All right, now we can make it further simplify this expression. Okay, so let's further simplify it. So this is going to be assumption 3. So we are saying that the gas, the pure component at pure component 1, vapor at temperature and pressure behaves like an ideal gas. So pure component vapor at T and P behaves like ideal gas, which essentially means that F vapor 1 pure is nothing but pressure, because that is what the ideal gas we have shown, the fugacity is same as pressure. Now, so that we got rid of the fugacity and put it in the pressure, but what about the FL? Okay. So that will be assumption 4. So we are saying that the effect of the pressure on the fugacity of liquid which is in the condensed phase is negligible, okay, within the range we are going to consider as far as the pressure is concerned. So the effect of the pressure is negligible for moderate range of the pressure. Okay. Now the second thing which we have considered, that remember that F2 is equal to F1 exponential, okay, integral of this, which for the liquid phase we can write this as this, right. So we are going to ignore this, and F1 would be can be replaced by simply F1 of liquid, okay, saturated liquid, okay, which essentially means that if we assume this F1 liquid, then we can consider that since it is at equilibrium with its own vapor for the pure, then this can be considered as the pressure or saturation pressure of it. Okay. So this can be replaced by the F1 vapor in saturation, and F1 vapor of that can be considered as a vapor phase. That means this can be replaced by simply P1 sat. So in summary, what I am assuming is that we assume that the vapor in equilibrium with pure liquid 1 at T is ideal gas, and we assume that this is nothing but 1, okay, that there is no effect of the pressure, and then we assume this. So this allows us to write FL pure 1 as simply P1 sat. Okay. Now we have written these two expression, we plug in there, what we got is a classic expression Y1 P is equal to X1 P1 sat. Okay, and this is nothing but Raoult's law, which holds within the assumption which we have made. Okay. So which means basically tells you that you can actually make use of the fugacity relations and apply these assumptions for a specific set of conditions. So with this I will just stop, okay, and we will continue gas mixtures and in general mixtures properties in the next lecture.